So I'm going to go ahead and start on the chapter 1 slides. I'm going to be working through the PDF file of my PowerPoint just so I can mark everywhere on there. You can follow along either with the PowerPoint or the PDF, whatever you prefer. So here we are in chapter 1, and we're going to introduce some key terms and just kind of set ourselves up for some of the concepts that we're going to come across later on in the chapter. So, at least from the perspective of a chemist, this is kind of the map of science that we think about, where chemistry really is involved in everything ranging from biology to physics to engineering to food science to medicine. Pretty much everything has connections with chemistry. So if we want to make a simple definition of what chemistry truly is, we'd say in chemistry we study matter and the changes it undergoes. So that's surely a very broad range of topics for us to consider, and one might argue that some of that clearly would fall more in biology and some of that would fall more into, let's say, physics, but we'll find our way and kind of talk about what we consider to fall into the realm of chemistry. So in the picture on this slide, you see the molecule H2O, water, in three different phases. We see it in the gas phase as an iceberg, as a glacier. We see it in the liquid phase, it's just the liquid water that it's floating on. And then we see it in the solid phase as the actual glacier. So the gas, I should say, is what's being emitted from the water through its vapor pressure or in the atmosphere. When we talk about matter, right, our definition said chemistry is matter and the changes it undergoes. Matter would basically be anything that has mass and takes up space. So that should really be a pretty wide range of things that we're talking about. So we're going to start here to define some terms that we were going to consider as we go along. Probably for the most part familiar territory, but we'll talk about all of it. So the fundamental building block that we'll get more into in the second chapter is the atom. So the starting picture is that atom basically is the smallest indivisible building block that we have. We'll find out that atoms contain subatomic particles later on. If we build something out of more than one atom, it's a molecule. If the atoms we use are the same, then it's a molecule of an element. When we start to combine different atoms together, then we're building molecules because it's more than one atom, but that would be a compound. What we'll find out is we can break compounds down to their elements through chemical changes. And the last thing we see here, it's just a mixture. So now there's a variety of substances. Here it's showing some that are just elements, some that are compounds. And a mixture is something that we can separate through physical means. And it turns out that's a lot of what a chemist ends up doing, just to purify whatever substance it is that they're looking at. So what we can also say is with atoms, these are our building blocks of matter, and we can consider a whole range of different substances that we can build with our atoms. So starting here, we've got oxygen. So now I've built a molecule out of two oxygen atoms. So that's one element, but it's built up into a molecule. Everything else on this slide is a compound because it's made up of more than one type of atom. So what you're seeing here is kind of a pretty standard scheme where hydrogen is shown in white, carbon is shown in this case either in black or gray, and then oxygen is shown in red. And so these are what we call space-filling models to describe what molecules actually look like in 3 dimensions. So we'll eventually, towards the end of the course, be able to turn a chemical formula into its actual 3 dimensional shape. That's definitely one of the goals. Just to give you an idea here with kind of what our model is telling us, right? For something like water, that would be our picture of that molecule. For something like carbon dioxide, that would be our picture of the molecule there. Again, stuff that we'll deal with much later on, but just so you can kind of see how these space-filling models work. And definitely one of the critical features of a molecule is what its actual physical shape is. We'll see that that will dictate some of its properties. All right, so this is a slide that we'll see a couple other times later on in the course as well, just showing the different states of matter. And so mostly what I want to highlight here are the degree of order in each of these states. So with gas, we think of things as being in total disorder with freedom of motion pretty much throughout whatever container we put them in. Liquid is substantially more ordered than gas, but much less ordered than solid. So we'd say that there's some disorder. Particles are free to move relative to each other, but they're close together, definitely compared to the gas phase. And then, of course, if we're talking about a solid, it's a highly ordered arrangement. Particles are in fixed positions and, again, close together. So we'll revisit this slide a couple other times when we start to talk about the gas phase and start to talk about moving between phases, so phase transitions. Okay, next we're going to talk about properties and changes of matter. So we'll start by comparing physical properties and chemical properties. So we're going to come back pretty soon after this and talk about physical changes and chemical changes. So that'll seem a little bit redundant, but properties and changes don't necessarily overlap throughout. Well, when we talk about a physical property, it's something that can be observed without changing a substance into another substance. So things like boiling point, density, mass, volume. So these are all things I can measure without converting the substance into something else. So boiling point, right, I'd be converting the liquid to the gas, but it's still the same stuff, right? If I'm boiling liquid water and I see vapor coming off of it, that's still the molecule H2O. It's just now in the gas phase. Or melting point, right? If I'm freezing liquid water and it's turning into ice, it's still the molecule H2O. On the other side, we have chemical properties, and chemical properties can only be observed when a substance is changed into another substance. So it's really talking about its chemical reactivity. So things like flammability, corrosiveness, reactivity with acid. So what happens when it's exposed to oxygen. Things where the observation of that property is going to result in it being changed into something else, right? If I light gasoline on fire, it's no longer going to be gasoline, right? It's going to go through combustion. It'll be a totally different substance or set of substances when I'm done. So that's one classification of physical versus chemical. Another separate classification we can make is intensive property versus extensive property. So a property doesn't need to be one of these four, right? I could have an intensive physical property. I could have an extensive chemical property. So these are just different classifications. All right, I think the easiest way to think about intensive and extensive is intensive properties are independent of the amount of substance that's present. So something like boiling point or color, that's not going to be determined by how much I have, right? At sea level, water boils at 100 degrees Celsius. That's not going to change based on the amount that I have. Density is something that we're going to think a fair amount about in the early goings of both lecture and lab. So density is mass divided by volume. And so mass is an extensive property and volume is an extensive property. What's an extensive property? An extensive property is something that does depend on the amount of stuff that I have, right? If I have more stuff, it's going to weigh more. If I have more stuff, it's going to occupy a larger volume. If I have more substance going through a reaction, it's going to involve more energy. So intensive properties are independent of the amount we have, whereas extensive properties do depend on the amount that we have. Okay, remember earlier I told you we'd talk about physical and chemical properties, but also physical and chemical changes. So kind of fits into the same idea here, right? A physical change is a change that does not change the composition of the substance. So we talked about changing from liquid to gas or liquid to solid or any phase transition, raising or lowering the temperature. Or if I had a gas sample, for example, changing the volume of the container with a movable piston. On the other side of this would be chemical changes. And like we said, if I'm investigating a chemical property, then my substance is undergoing a chemical reaction. So chemical changes. Combustion means igniting something in the presence of oxygen. Oxidation would be like rusting, right? If I leave something in the presence of oxygen for a long period of time, what will happen to it? Like the same as like if an apple starts to brown. Decomposition would be breaking a substance down into its component parts. Like for example, when you use, say, baking soda in a bread to make it rise, when you put baking soda, sodium hydrogen carbonate, into the oven at 350 Fahrenheit, let's say, it breaks apart and releases carbon dioxide. So that would be decomposition. So kind of highlighting the same idea as before, right? A physical change means I've done something that doesn't change the substance into something else, whereas a chemical change means I have changed it into something else. So as we think about chemical changes, we can use more technical terms, and now we're talking about a chemical reaction. So the reaction we're looking at here is we're taking hydrogen, reacting it with oxygen, and forming water. The hydrogen and oxygen and water are all in the gas phase for the purpose of this experiment. So that's what those are for. And we'll talk about balancing equations in the second section, but all balancing really means is that we need equal amounts of each atom type on both sides of the equation. And it turns out to make this particular equation balance, we need a 2 in front of the H2 and in front of the H2O. Just if you're looking at what's going on, right, there are 4 total hydrogens on the left side, 4 on the right, 2 oxygens on the left side, 2 on the right. And we'll talk about that in the second unit. And it says again, in the course of a chemical reaction, substances are converted to new substances. Okay, here's our balanced equation on this sheet. And so now we're back to the term compound. And I think I said this earlier, that compounds can be broken down into smaller particles, into its component parts. So let me go back for a second. Right, the reaction we were talking about, this is actually the combustion of hydrogen to make water. Now we're flipping it around, starting with water to make hydrogen and oxygen. So this is a kind of common apparatus for generating oxygen. You just have water as your source. Uh, we've got a power source here in this electrolysis machine, which basically provides energy to break the water molecule apart into its components, and it leads to the production of oxygen. So like for an oxygen breathing device, you could just use water and a power source to generate oxygen as needed rather than carrying oxygen around, which oxygen is really flammable, so that's fairly dangerous. But anyway, what we're observing here is a chemical process where we're breaking down the compound into its elements. Okay, this is a chart that I've also provided to you as, I think, handout 1 in the on the Blackboard page, just kind of talking about some key ideas. So what we were looking at just now was our pure substance, water, and let me write it down here actually as our compound, and then we broke it up into its elements, hydrogen and oxygen. So what we're looking at there is separation by chemical method. So we ran a chemical reaction, provided energy to that reaction in order to break things apart. Just let me go back real quick, right? So we've got water and we've got this battery as our power source to cause the water molecules to break apart into hydrogen and oxygen. On the other side of this, we're talking about mixtures and separating by physical methods. So we'll look at a few physical methods in the next few slides, stuff like distillation and filtration. Two new terms on this page, homogeneous mixture and heterogeneous mixture. So homogeneous mixture means that the composition is consistent throughout. So if I dissolve salt in water, if I dissolve sugar in water, that would be a homogeneous mixture. The air in the room, that's a homogeneous mixture. So that means that the composition is consistent throughout. On the other side, we have heterogeneous mixture. Heterogeneous mixture means that the composition is not consistent throughout. So probably since the first time this idea was thought of and written in a textbook, the example for a heterogeneous mixture has been trail mix, where we just say, if I grab a handful on one side compared to a handful on another side of the jar, I'm going to get a totally different composition. So that's what homogeneous and heterogeneous mean with regard to mixtures. So I just want to give you a couple examples of physical separation methods that we would typically do in the lab. So this doesn't really apply to lecture stuff that much, but interesting nonetheless to think about what physical separation really means. So I'm just highlighting two ideas here. One is distillation, and distillation is for liquid separation typically. We can also distill something like salt water, where we get the water to stay to boil and the salt to stay behind. So just generally speaking, if we're looking at what's going on in this picture, I've got my heat source here, the Bunsen burner. So that's heating up the water in my flask. So the salt is not going anywhere, right, when I heat it up with the burner, but the water will. Sodium chloride has a very high melting point, so this Bunsen burner is not going to have any effect on it, and it's certainly not going to vaporize it. But the water is going to travel up through the flask to the top of the flask, and then what you see here is I've got water circulating through this condenser, And it's kind of, I guess I would call it a jacketed condenser. So the water is circulating on the outside, but there's a path down the middle of the condenser that's not touching that water, but it's cooled on the outside by that water. So essentially the hot water vapor comes into contact with the cooling on the exterior, and that condenses it back into liquid water. It travels its way down and then collects into our receiving flask. So that will leave the salt behind and the water will be collected. So that's what we mean when we say distilled water, that we've distilled it through this kind of process. So, of course, that would work great for removing liquid from a high melting point, high boiling point solid, but also I can use this method for a homogeneous mixture of liquids as well, so I could separate two liquids from each other. Another pretty common separation method that chemists do a lot of, and you'll see it in the lab a bit, is filtration. So filtration, that's when I've got a solid and a liquid to separate. And so it depends, right? In certain instances, I'll be trying to keep the liquid and get rid of the solid. That's when I typically do something called gravity filtration, which is kind of what's going on here. You could do it to keep the solid, but it's not as efficient. And on the other hand, if I'm trying to keep the solid and get rid of the liquid, I do something called vacuum filtration. But of course, this is suited for a heterogeneous mixture where I have solid floating around in the liquid and I can separate it by a filtration method. All right, so I'm going to go ahead and stop here with this first video. So this is kind of my plan to try to make, I don't know what these are, 20 to 30 minute videos each time. And then there's a homework that goes along with each one of these segments. So hopefully so far so good, and I'll go ahead and stop this video here.